With questions. As a chairman, you can go and ask you to come back. We're about to start. Hey, down in front. Okay, so last but definitely not least, we have Vyacheslav Spiridonov giving the last talk of the session. He'll be telling us about some new limiting forms of the elliptic hypergeometric functions.
Thank you, Eric. So, elliptic hypergeometric functions emerged as a principal new class of special functions on the turn of millennium. And it was a very hot topic at that time, and this Japanese society decided to organize a special meeting in elliptic integral systems, and in particular attached to this new subject was this new class of special functions. So that was the first meeting in the series. The second one was organized by myself in Max Planck Institute, and I was also co-organizer in the fourth and fifth, and I perfectly well know how much effort it takes to organize such a meeting. So I would like to thank Japanese organizers for doing it for this time. So thank you very much. I especially appreciate what you did by putting this relation, which you saw already on the poster, taking as a workshop logo, maybe the logo for the whole series of the workshop. You did it a little bit in a different way, namely you take this a prefactor, which is here, I put on the left side, in your case it's on the right side. It's a little bit wrong in the sense that in this form, this is a very nice group theoretical identity, expressing some very nice relation between so-called superconformal indices and four-dimensional supersymmetric field theories, and so, but it has purely group theoretical explanation, and it actually confirms the confinement phenomenon in some particular supersymmetric four-dimensional field theory with the symplectic group and with some SUA cross U1 flavor group and so on. So quite fundamental from the physical point of view, and proof it goes towards the so-called BPS sector. And why I'm so happy that you took it, because this formula for this relation was discovered in his hands within the joint project with Van Diezen. And later, again with Van Diezen, myself alone with Ole and with Eric's contribution, many similar formulas have been found, and so, but much more was found by my joint papers with Vartanov, and exactly this relation with superconformal indices was found, and many of those relations are still conjectural. But the source, the origin of all these types of relation is a univariate relation, this one, and in one case, which is the univariate elliptic bit integral, which I exactly discovered on the turn of the millennium. And if you ask what kind of most general exact integration formula is for the Gaussian integral, here it is. What is the exact most general generalization of the Euler bit integral? Here it is. And you can continue such type of statements, so it can be considered quite a fundamental relation. And in particular, it is attached to the E6 root system, and somehow, so quite unique object. So this is, as you see, on the right-hand side, you have the product of triangular product of elliptic gamma functions, and its kind of meromorphic function on the punctured plane. How we compute the integrals of contour of meromorphic function? We squeeze the contour, capture the residues, and look what you get. What happens if you do this with this integral? You get the following relation. So the integral has the poles at these points, so double geometric progressions for each variable, and you squeeze towards zero the contour of the integration. Here what happens? You get the sum of 6 terms, some product ratio of elliptic gamma functions coefficient, and then you have the product of two elliptic hypergeometric functions, which I denote as 10 V9. They are infinite, because you have infinitely many poles and residues. So what is here, you see one of the parameters from 1 to 6 is absent, exactly which you count, A. So absent is the square parameter in this case. And one of the parameters, any one, is actually escaped in the first B function by P power, you divide by P power, and the same here. One of the parameters you divide by T by some Q. And here's the definition of this infinite tangent series explicitly, and this is the ratio of the functions you saw. This is the ratio of elliptic Hammer symbols, also you saw these relations. I use a little bit different notation than the one appeared in Helmerstock, but it's in the spirit it's the same. So this is the balancing condition. And the big question is that, okay, we did it formally. Actually, I knew this formula from a very long time, but didn't publish because it's purely formal. You cannot say anything like what's the meaning of this relation until you prove that it exists in rigorous mathematical sense. That's what I would like to discuss now. Is it possible to give any sense to this relation in terms of the series, not in terms of the integrals? Because integrals are meromorphic functions, and as you will see, the singularities of this infinite elliptic geometric series are very awkward and wild, and how it may happen that this sum of very wild singular functions gives you a nice meromorphic function. It is not known, but what we can say around this problem, it's the following one. Of course, you have to analyze the convergence problem of this type of series. And let me remind you, let me take some irrational number in the unit interval, and denote by this curly bracket the fractional part when you multiply this number by integer, positive integer, until infinity. Then, according to Hermann Weyl, definition of the uniform distribution sequences on this interval, for any irrational chi, this sequence is uniformly distributed, which means that for any Riemann integrable bounded function f of x, you have the following relation. So sum of this type, when n goes to infinity, converges to the integral. And this type of relation forms the basis for the Monte Carlo type of computations of various integrals when you replace integration by random coverage of space and replace integrals by sums. It's exactly the same. And for periodic function, you actually can remove this fractional part and get this relation without any mentioning that this is some kind of taking module 1 relation for the products. In 1946, Hardy and Littlewood considered the following problem. They took the simplest Q hypergeometric series, this is 0, 5, 0, of this form, this is the Q Hammer, and asked whether such series can converge if Q lies on the unit circle, not the root of unity. And the answer was positive, and they have proved that if you restrict the value of chi to some particular irrational number such that the consecutive candidate fraction convergence satisfies this relation, so the number, this convergence do not rise too fast, and it's very sparse set of numbers. Actually, all numbers such measure 1 of course satisfy this condition. And so for almost any irrational number 1, the radius of convergence of this series is equal to 1. Because you can estimate in the following way. So take the coefficient of the series modulus, this one, rewrite it in this statistic exponential form, where f of x is log of this function, simple elementary function, and replace them by integral. You will get this asymptotic, leading asymptotics, where RC is just integral of this function over unit 1 and it's equal to 1. So this series converges despite of the singularity emerging in the denominator, which seemingly blows up, but the fact that if z is smaller than 1, it falls down faster, and the series converges. That was a very nice result in a sense, but almost never used in any application. Although it was discussed by mathematicians, it proved extended to some way. Okay, let me consider what happens if you go to the elliptic hypergeometric series. So, at some time, I have defined this series in the following way, which Hjalmar mentioned, and investigated all structural elements which can be embedded into it to make it work in some various constructions, in particular applications. So this is a general elliptic hypergeometric series with many parameters, the numeric denominator, with one of the denominator parameters chosen especially to be equal Q, because when you replace the elliptic Hammer by the ratio of elliptic gamma functions, then automatically this series terminate from below, and so it becomes univariate. Not bilateral, but unilateral series. And here is the balancing condition, which you already saw many times. So if we take now the sequential ratio of these coefficients of this series defined here, then you will get the following function. So Hn, which is the ratio, is equal to this elliptic function. That's the essence of the definition of elliptic hypergeometric series. And this function satisfies this relation that HPU equals to HU, it's P elliptic. And the point is that for generic values of P and Q, the sequence of points of this type, where M goes from full set of lattice integers and this is the positive integers, it starts to fill the tori completely fully. So essentially when you have a non-commensurate situation, the coefficients Cn divided by Zn is given by the product of this function with U replaced by powers of Q, and it's walk over the tori, over the torus, and if in the incommensurate case, you fill tori completely by the poles. So it's widely a singular object when n goes to infinity, when the number of products goes to infinity. And what kind of function then you emerges? It's a big question, it's open and it's not known. And so what we did with my co-author, Krokov, I should mention that this I reported paper by joint with Krokov, and also later we'll mention also some results joint with Sarkisian. And we fixed the Q now, not generic one, but for this specific form. It's Q in the power 2 pi chi, this irrational number, times n integer plus n integer, and tau is the, P is exponential of 2 pi tau. So essentially, it's parameterization of Q, and P is the parameterization of P. Why it is so specific? You take the lattice at elliptic points, and between 0 and any point which has coordinates n and m. Put the line through them, and force your sequence of Q to the n lie on this line all the time. That's the point. It means that on the tori you choose particular curve, closed curve, and you walk only around that curve, so that there's space left analytical in a sense in some parameters. And then this function, this h of u, which is h of qk, well, you simply estimate the coefficient. You do the same trick. Now, as it was done by Hardy and Littlewood, here's exponential, and again come to the same relation where the radius of convergence is given by integral of logarithm of this elliptic function with this such type of choice of parameters. And you see, I have replaced here this power of n chi by x, exactly as y did, and this function is periodic with respect to x shifted by 1, because shifted by 1 is equivalent to multiplying of this argument by p in the power m. And it's p elliptic, so it's periodic, and while relation works. Since this function is factorized as a product of theta functions, then the problem is reduced to the computation of this simple integral, one block. And it is computable. So an integral from 0 to 1 logarithm of the theta function of x, where it's here, and two integers, and p is parameterized by tau. If you take m bigger than 1, it goes as follows. You first pass from the base p to the base p in the power m by artificially introducing additional summation in the powers of p. Then you use the this triple product, Jacobi triple product. This is the definition of this short theta function. Here is the infinite product is replaced by infinite sum. You see from 0 to 1. Then you notice that these objects which appear here, x plus n and n plus 1 minus x, actually this x to 1 minus x symmetry reduces to this term, and now these are equal terms, only these guys are different. So we come to this such type of sum of integrals from 0 to infinity. You see here it was 0 for 1, but because of the summation over n, it becomes integral from 0 to infinity. So essentially that's what you need to evaluate. This integral with g of x, even by this logarithm of two elementary functions. And it was computed, just expanded into the series, and integrate, and surprise, come to the logarithm function. And here is the final answer. So there emerges this parameter mu, which is modulus 1. and it has the argument of t function and this particular additional phase factor. And logarithm square, so nice answer in terms of the logarithm function. Next, this so the final result will be the following. If there are non-trivial greatest common divisors for these numbers, then this integral can be written in the following way. Essentially, you sum up over m. That's the final result, or in this case. So now some polynomial in m, and here is the logarithm. If n equals to 0, you can get the same formula using the modular transformation for theta function. So it works even for n equals 0 case. And here's the number theory trick, which helps to push it towards a very simple answer, towards the polynomial of the second order. Since our mu has modulus 1, so the argument lies on this interval, then the real part of the dilogarithm given here is directly related to the Fourier transform of the Bernoulli polynomial, second Bernoulli polynomial. And so with this very simple computation shows that the real part of this dilogarithm with the pure phase is nothing else than the given by the Bernoulli polynomial. So actually this guy is replaced by this quadratic polynomial, and the full answer now is the following one. So theorem. First, I didn't mention it, but the result which I state now, it touches the case when t equals to q. T is not equal to q. In this case, we cancel this the dangerous denominator factor, which for roots of unity goes up. If you choose one of the parameters equal to q, you just cancel it out. In this case, h of u is not singular, and so this function which you integrate is periodic without singularities, and while theorem works perfectly well. And then this is the radius of convergence for this series without any restriction on chi. And it's given, as you see, by the logarithm square of parameters. Here is the quadratic polynomial of alphas and betas, where alphas and betas are particularly fractional parts of these combinations of logarithms of parameters and this n plus n tau. So very nice, simple quadratic expression for the radius of convergence. If you somehow will want to remove this constraint, take this for singular case, then you need this hardly eliminable restrictions for chi, and the same formula works, and you with the particular choice of alpha not equal to 0, which corresponds exactly to this fixing that one of the parameters is equal to q. This is for general elliptic hypergeometric series without further structural restrictions. First important restriction is the well poisedness. It comes from the following constraint imposed on this series. Then if you impose this constraint in this formula, then the first term cancels out, the things simplify, and everything is reduced to some, you introduce some particular parameterization of these parameters, so you take out powers of q, and these additional powers of some combination of tau and n. It's a kind of similar to the decomposition of the complex number to the modulus and the phase, but using q and p essentially parameters. And then everything is determined by these 5 numbers, which satisfy this is balance. This is the well-poisedness condition. This is the balancing condition. The formula takes now this simple form. Analyzing this formula, we have found some particular sets of 5 values which show that the series converges for a radius of convergence bigger than 1, which is important because many formulas exist for z equal to 1, and we show that there exists values of parameters for bigger than 1 radius of convergence. Okay, and final thing is to consider the very well-poised series, which is the most important case when you choose 4 parameters, restrict 4 parameters straight from the back to particular 4 values, and then the ratio of 4 elliptic hammer symbols reduces to the simple factor. This is called very well-poisedness condition. The balancing condition now takes this form, and you particularly fix this z value, z parameter, which I was using as a power parameter for the general case, 2 equals to -1. And you get this very well-poisedness series, which exactly emerges in the 1039 case in this elliptic graph. What happens for them? And it appears that the same, now you do not use the same formula, but you compute in u this radius of convergence for this h of u function, ratio of determining ratio of coefficients. The balancing condition now is written this way. And so you just repeat the same thing for this particular HOU and come to this formula. This one of the terms survives. What I didn't say is the following point. That okay, I skipped it too fast. In this case, yes. In the well-poisonous case, if all these numbers phi, fractional parts, coincided with these numbers themselves, then the radius was equal to 1. That's I forgot to mention, that why we were considering a radius of convergence bigger than 1. In this case, just 1. But there exists a set of values when it's bigger than 1. And in this case, in the very well-poised case, it's somehow situation much simpler. This term survives. And if we now demand that these phi numbers, the same parameterization as before, this is the balancing condition, this is the balancing, this is well-poisonous, and the very well-poisonous restriction leads to the following term. And even for this case, when fractional parts of these phi parameters were equal to themselves, then radius converges bigger than 1. So for this particular restriction, using also Hardy-Little type restriction, the very well-poised elliptic hypergeometric series does converge. So which was quite surprising to learn about. And so it gives some hope that there can be given meaning to some infinite elliptic hypergeometric series identities. And so that's the main result in a sense of our work. And going further on, we can apply it to the computational asymptotics of Frank-Troyer sum. So it's when you terminate this 10v9 series by choosing, say, T4 equal to n minus n, then it terminates with only n terms, and it can be summed that it's given by particular elliptic function. This is a ratio. It's a ratio of elliptic polymer symbols. For when p goes to 1, this is nothing else than the Jackson sum, is well known. And the Jackson sum for n goes to infinity goes to 6W sum, 655 sum, and this is the full exact summation for 655. And it doesn't exist in this form in the elliptic level, but what exists? Using our results, we can now estimate this asymptotics of this Frank-Troyer sum for some particular choices of parameters. So here is again the same trick. You use this. Essentially, what you do, you consider the asymptotics of particular elliptic functions, and the number of the order of elliptic functions goes to infinity along very particular choice of poles. That's what you do. And in this case, it can be done, and you come to the same formula now. You have to compute this integral for this type of function, determined by the Frank-Troyer sum, and you get very simple again result. Now only these terms. No, it has different form because it's not this term in the series; it's the result of the summation of the series. And looking at it, one can see three different regimes. First, if the integral vanishes, which happens if I can replace to remove the fractional part, then the integral vanishes, and you cannot estimate the asymptotics. You only can say that it is not exponential. It's some exponential in all small of n. That's all you can say. However, if you see here, you have now broken this condition, and for this particular choice, you see that it goes to 0, vanishes. And for this particular choice, just one example, this some exponential blows up. So you see, its behavior in quite a nice, interesting way depends on the arithmetics of your parameters. Essentially, what I want to say is that these are kind of fractal functions, and the structure would be very nice to understand from a more general point of view. For the moment, it's just a work in progress, and somehow I announced the result that it's possible to apply the results in this direction. But next, second part, degenerations. That's the main topic in a sense. So many degenerations were considered by people. Elliptic hypergeometric functions. Let me mention very briefly from two trigonometric one. When the elliptic gamma function is reduced to this Q product, then you go from elliptic to Q hypergeometric integrals in the trigonometric sense, and which can be further degenerated to the rational case, ordinary gamma functions emerge through this Jackson gamma function limit. And so this is well known, and we won't tell it. Elliptic 2 hyperbolic was considered by Roshinars and proved by Reins to be uniform in the compactor, which is very important for application to the integrals. And in this case, the elliptic gamma functions, both P and Q go to unity, including the parameters. All the parameters go to unity. You see how it works. V is here, V goes to 0, and then suddenly you have blowing a coefficient, and this is what is called Faddeev module algorithm, or hyperbolic gamma function, or it's 1 over Shintani's double sign function, names. And here is the exact definition. So it's given by some exponential Bernoulli polynomial with the second order multiple one, and the ratio of two infinite products, where Q, fat Q, is now mu Q, and it's defined through the ratio of this omega 1, omega 2, which I replaced by P and Q. So you see it's different. Q not in the previous one. That's what emerges. And now new limits. What you can do with this? It appears that a very special choice of this omega 1, omega 2, which breaks the relation to this Barnes gamma functions and zeta functions, it simply exists as those functions. When the parameter, these quasi-periods are opposite to each other, omega 1 equals to minus omega 2, and then everything blows up in that setting. But because you work with the ratio, the limit takes the following form. You take the parameterized argument in a very special way. This is an integer. This is delta is small. You can take it to 0. It's complex number x, and this is normalizing parameter. You see it's complex. Then suddenly it blows up. Of course, it should be of the business factor. And here is the ratio of gamma functions, which is called gamma function for the complex field of complex numbers. And such type of objects emerge already in the Fangrave and the Lemkin book, but it was never used by people, and so it was lying until recently without touching. And in fact, that was the reason why I was so much involved in this business. I had known at some point the existence of the complex hypergeometric functions. My question was, where they lie in the elliptic world? And it appeared that they right directly there, just particular limit should be taken, which is this one. And you see the ratio of square root of ratio is I, which means that omega 1, omega 2 is minus 1 plus some infinitesimal complex number. This is result rigorously established by Sarkisian. Early in very ad hoc manner it was given by these people, but during our work we have found another similar limit. So when these omega 1 and omega 2 are parallel to each other, equal to each other, but you choose the parameterization of the argument also in a very special way, then this hyperbolic gamma function degenerates to plain Pohammer symbol, again with some blowing factor. And this leads to, again, to new degeneration of these hyperbolic integrals. So, what happens with the elliptic beta integral when you degenerate to the complex case, in the complex numbers? It's a formula of this type. Sum over infinite bilateral lattice of integers with some very acute parameter nu, which takes 0, or basically it's a summation of integers and half integers. And then goes to this type of formula where this is a simple quadratic polynomial, and this is the product of complex gamma functions, and it's exactly a computable object. You have the same triangular product of gamma functions, generalized gamma functions on the right. The balancing condition has split into two pieces. So integers satisfy this one, sum is 0, and these complex numbers alphas sum up to some particular complex number. In the rational case, you have the following situation, the second singular limit. You have again the same type of summation, some integration over real line in this case also, and you have again similar looking expression, but now you have these simple Pohammer symbols. And this contour separates the poles which emerge from the choices of plus, poles appearing from plus sign and from poles of minus sign. It's easy to see that for a sufficiently large m, all poles lie either up or down of the contour of integration, which means that actually this is a rational function, and summation terminates, and actually this is the rational function given by this product of rational functions. That's why I called rational hypergeometric function, because this is a new kind of formula between Pohammer symbols and the pure rational level. But it's hypergeometric because it involves these Pohammer symbols. These results have led to the new rational degeneration of the Van Dieven model, and rationales also. And it goes as follows. You apply this single degeneration to hyperbolic level of Richness and Van Dieven system, and come to the following Hamiltonian. It's exactly the same formula expression as rational Van Dieven case. because this potential is just pure degeneration of the Van Diegen's potential. But the parameterization is very different, because you see these variables which emerge here, parameters, they involve both integer part and complex part. Integer part, complex part. And they satisfy these now two balancing conditions. And the point is that this operator is now self-adjoint with a very different type of measure. It's not now the single integral, but it is now a bilateral infinite sum of integrals of the Mellin-Barnes type. This is the measure for complex hypergeometric integrals. And this is the measure for this particular operator. And so I won't describe this structure in no time, but it looks similar to the previous simple univariate case formula. But now you have, of course, much more parameters involved. The number of parameters is exactly as in not exactly, it's actually not fully general Van Diezen model, it's so-called balanced Van Diezen model. So that's a new degeneration of rational degeneration of the Van Diezen model, and the most important thing is that you see the measure. Measure is very strange for those who didn't see such type of measures before. It's an infinite bilateral sum of Mellin-Barnes type of integrals, and it sits inside the elliptic hypergeometric business. And the special subcase of this measure can be computed when you apply it to unit functions. I won't describe it again in details. What you get a new degeneration, a new form of this limiting form of this conference log formula. This is type 2 elliptic beta integral on the CN root system, and this is a new form. And again, two balance conditions, so constraints, so it's exactly computable formula. So with Lord Sarkisian, we have some also considered many formulas, multivariable formulas as for in these limits, and somehow I won't talk about that, but it's just claim that it was considered. Final thing, I would like to present a scheme of classical special functions in the view of these limiting cases. So in 2003, I have shown that the univariate so this orthogonal polynomial business can be shifted to the biorthogonal rational functions. That was shown by Wilson, and the same Wilson as the Wilson polynomials case, and Rahman. And the Q hypergeometric case, it was involving 10 finite functions in the Rahman's case. Together with Zhdanov, we did it for the discrete measure case in the sense of elliptic analog of the Racah polynomials. When you have a discrete measure, it's finite dimension, and so on. After discovering the elliptic bit integral, I generalized all this stuff to the continuous measure case, and here's what happens. You define these 12v11 functions with particular parameterization of arguments, and do the following trick. You define a partner just by permuting two parameters, entering this parameterization. T6 and T5 you permute. Then you form this double product for R's and T's, which are symmetrized by in QP. You see here no symmetry in QP. This is symmetric in QP, and this. And then you get this biorthogonality relation. So the product of these two integrated over elliptic bit integral measure is exactly computable, and here are double Kronecker symbols, which means that you have, for univariate special function, we have two-index biorthogonality relation, which is completely new phenomenon in special functions at that time. And here are the normalization constants, some particular choice of the contour should be taken, not to clash with the poles, I won't describe it. So that was a new set of elliptic hypergeometric orthogonal functions. You can do now the same degenerations. I won't do this trigonometric and rational case. I will do immediately at this hyperbolic and further on. So also at the same time, I consider the degeneration to the approximately at the same time. I consider the degeneration to the hyperbolic case, and what you get the same structure of orthogonality relations with the measure given by this general hyperbolic beta integral, which was computed first by Stockman, and but it is obtained as a limit from elliptic beta integral. And here are again some structural elements, so it looks the same structurally. And for a very long time I was wondering why it stops at this level, why 10v9, 12v11, and no plane hypergeometric objects. And only now, after working with this complex hypergeometric objects, it became clear what that there exists also the plain hypergeometric case of this type of relations, and you have to go to this complex hypergeometric business. And when you apply this limit, when this omega 1, omega 2 in the hyperbolic case, their ratio is -1, you degenerate now this 10 F9s or 10 W9s which were there towards the very well poised to balance 10 F9N functions with the particular parameterization of these arguments. And here how it works. So you have integration and summations hidden in this Y variable, which is now you see integration variable here and summation variable N. And Y prime is you just change the sign of N. In A is again it's parameterized in this way. Y prime is you change the variable discrete variable. So you see it's kind of symmetry in this of such type. And again the same bilinearity, computation of the things, some restrictions on the contour. So it works, which I'm very happy to understand. And here is the final scheme of classical special functions. So Jacobi orthogonal polynomials is just left corner. It's Euler-Gauss hypergeometric function involved. Then it goes various generalizations by Rogers in terms of the hypergeometric function. Then by Chebyshev to 3, and Hahn. Then Raka and Askey-Wilson. This is the top level of the orthogonal level. Askey was considering various limiting cases, and this is called the Askey scheme, but after the discovery of Askey-Wilson piece, it is called Askey-Wilson scheme, and that involves all classical special orthogonal polynomials, and many names, huge, thick handbooks exist of these limiting cases. And what I am suggesting now is the completion, or extension, generalization of this scheme towards this bi-orthogonal rational functions case, which is this level when you have only one single thing. And this is now not bi-orthogonal rational functions. Bi-orthogonal, but they are not anymore rational functions. You go beyond even rational functions at this level. So there exists now this 12-11, as I said, in a discrete case was done together with Zhdanov long ago. Next year I did continuous case, and also realized that there is a symmetry in PQ, and so it's a bilinear actual thing. And you see how big gap is between this scheme. For a very long time I was showing this scheme without this piece, and now it finally completed this scheme and somehow fulfills the part of my program of the findings of kinds of special functions, classical special functions. That was important. But this is, of course, not all that is possible. I will not mention many things. I will mention what goes up from this level. From this level up, it goes, for instance, these what I call rarefied hypergeometric functions. They are attached to length spaces. The ideas came from physics to go in that direction. So I just worked out rigorously various things, and in particular, established the elliptic hypergeometric equation in this setting, and things like that. And for instance, together with Sarkisian, we have found the orthogonality measure for this type of objects. So not functions, but orthogonality measure for this would be length space functions. For the full general length space has been computed, so we have some good step towards that direction. And quite a lot should be done for lifting all this up to this list. But also, again, this is not the whole story. There are some Seifert manifolds can be extended from length space, and a long road ahead with many exact formulas of such type. So quite a lot of work. And even more, there are other types of things to be considered within this big Everest of special functions. And this is just one of the mountains. It's a K3. So
length space for all P and Q? Length space for all P and Q?
Yes, we did for general length space at the hyperbolic level, univariate case. So it's clear how to generalize it for multivariable case and then go for the more general functions, but good work it should be done. So that's all, and this is a good point to finish with this scheme, because somehow completion of some program is nice to know. Thank you very much.
Are there any questions?
Maybe just a remark. Shouldn't all your arrows point in the opposite direction, Slava? That's,
Good point.
So,
Timeline.
no, it's that the bottom left was broken.
Okay.
There's not even-
Generalization, so the volume goes up, this is inverted, let it be like that. The point is that, yes, I was meaning exactly the generalizations, not the generation bugs. So the ASCII-Wilson scheme gives you the way back. So you take this and slowly go down, splitting big mountain to the small mountains, hills, eventually flattening towards the Chebyshev's polynomials. Not much done in this case, in a sense. For instance, this is now completely new, you have to now investigate. Even this is not completely in a sense, because I have to check everything, publish and whatever. It's just announcement at the moment. And things like that. And so opposite lining is part of the good work.
Any other questions? Well, I have one. Do you think it's likely that, back to your first limit,
Yes.
do you think it's likely that there's going to be identity, like an evaluation for infinite Frankel-Turayev sums, or maybe like sum of product of two of them or something?
That's the aim of that first part project, to try to understand whether it is possible to give some meaning for the infinite series type of identity. For the moment, it's not known, it's work in progress, and all we did, we found particular domains of values and parameters when the one series does converge. Whether the second series does converge should be analyzed, and if it is analyzed, if it does converge, then the interesting problem arises to explain how the infinite sum of poles at each line disappear. There must be some particular cancellation of sums of radiuses of these poles that kill them. Because this series which I have, they are analytic functions with natural boundaries of the parameters. If you take, say, one parameter, and each coefficient of this series, the first coefficient is an elliptic function in one parameter of the second order. Second is the fourth order, 6th order, 8th order, and so you add each time when you multiply additional two poles. And so all these poles lie on one line, and which forms exactly the natural boundary for. But in between you have meromorphic, so it's analytical. So it's not. It's of course periodic, but not elliptic, no meromorphic. And how this singularity will be killed on this natural boundary? I have no idea, and it's a big question. But first you have to prove that everything is fine with that. And it is to do it rigorously, extremely hard problem.
Also, do you think it's likely that you would have convergence? I mean, you're sort of looking at convergence in a case where all your poles, I mean, Q is basically just filling in a line, but of course typical Q is going to be filling out the entire torus.
Yes, that's another part of the story, and for the moment we didn't touch it at all because it requires now two-dimensional wild-type theorems and their uniform convergence, uniform distributions, and the generalization of the Hardy-Littlewood approach to the two-dimensional case. So it's very tough for that type of approximation analysis, which I'm not expert in absolutely, but I have to do it if I want to understand these things. At the moment, I was able to do it with my young colleague, understand only just a linear case. But of course,
I mean, I think it might make things more symmetrical between P and Q.
yeah, but then the type of singularities now becomes much more wild. Okay, that's.
Any other questions? All right, well, let's thank Slava again.
I did it exactly in time.
I think we have a 16-hour break. No, sorry, an 18-hour break. And I think there's a dinner or something.
Today we are going to have a conversation Banket will start at 6. We can have slowly. This one starts. Okay. dynamic stuff that we don't know the geometric also ASCII or local So basically, if you does not know the way to go, just follow me and take some good. Follow him, not me.
Of course.
We would like to ask you to pay fee 3,000 yen in front of the restaurant. And in addition, due to some unexpected reasons, we also would like to faculty member to ask some amount of donation for mainly alcohol. Because our budget doesn't cover any alcohol drinks. So yeah, please